Hi everyone. Today I'm going to talk about the TP4056 1 amp linear lithium-ion battery charger, a deep dive into the operation of this IC. So I'm going to bring up this data sheet and just talk about the general features before I go into the actual details of how this chip operates. I'm not going to spend much time either in the detailed specs, but I'm just going to quickly go through the features, so bring everybody up to speed if you're not that familiar. But ideally, it's not a video about how to use this chip or the tweaks or any of those kind of things. I think there are a lot of people who have spent time and effort into describing how to use this chip and how to modify it, or play with different features besides under voltage protection, over discharge protection, and so on. So this is very simple uh, video about just the operation of this IC. So I didn't find too many videos that went into the details of this. I did find a few, but I thought I would give it a shot myself. So hopefully you find it useful. So let's just go over the brief features. One is it's programmable up to around 1 amp of current. I think the external resistor R program allows you to do that. There's no MOSFET or sense resistor or blocking diodes required externally. It's all internal. The complete linear charger is an SOP package for single cell lithium ion batteries. So it's not meant for series cells or that kind of application like a BMS, but more or less for charging a single cell. And of course the current is limited to 1 amp, so if you want to increase that you have to do other things, put external stuff or overdrive it, cool it, and so on. It has both a constant current and a constant voltage mode of operation. Thermal regulation, I think it's pretty robust. The way I was stressing the chip, I don't think it had any issues with that. It can directly charge a single cell lithium ion battery from a USB port. That means it accepts 5 volts and all the way up to 8 volts if you apply a different external power supply. And it charges up to 4.2 volts, which is preset, and it's fairly accurate. I did measure that. It's 4.2 plus minus a few tens of millivolts, I think. There's a charge current monitor for gauging. I'm not sure what that gas gauging is. I think it's just a charge current monitor. It's got automatic recharge. It's got no fault status display, no battery and fault status display. Okay, 1/10 charge termination, 50 microamp power supply current in shutdown mode, and the 2.9 trickle charge threshold. So that's when, if the battery voltage is less than 2.9, it actually will only charge it at 0.1 of the maximum current. Above that, it will allow you to charge at the full Imax current. And it's got soft start, limits inrush current, and battery temperature monitoring function. So that's also built in, also with an external means to regulate or to check the battery temperature and then allow this chip to shut down and so on. So it's got quite a bit of features. I think it's generally well designed chip. I think it's robust. It doesn't mind short circuits, and I think it's definitely a better than average chip for that, for what it's designed to do. I think it's based off the TPC 40, sorry, I'm not sure, the LTC 4056 chip from Linear, and I think it's a little bit different, but I think it achieves the same thing, except that this got a built-in MOSFET which allows you to charge all the way up to 1 amp, whereas the other LTC chip is more or less a trickle charger. So next I will go into the deep dive really into the details of the innards of this chip. So let's get to that. So here's the TP4056 internals. This is from one of the manufacturers that that has released their internal block diagram. There are many others. Subtle differences in terms of how they have, what kind of ratio they have used here. A few other supervisory circuits, slight differences in those, but essentially this structure is the same for all these different clones of this version of this IC. So let's first talk about the pinout. We have the, starting from here, the VDD, you have the battery which connects to the lithium ion cell, the ground. You have a programming pin which can be used to either shut off the chip, or you can use it to set the current limits using the external R program resistor. There's a charge bar which indicates charging when this is high, when this is low. This pulse allows this LED to come on, and then similarly for standby. Then you have the chip enable, which when turned on high actually powers on the chip. And there's also a external temperature control pin. There's also an on-chip over temperature, but this is not brought out, or it's internal, so I just shown it without any pins. So that's all the pin out as far as this chip is concerned. There are 8 pins. So next we'll talk about the digital functionality. So we mentioned the standby and the charge signals, which are available as external pins, which if you tie an LED to a suitable resistor, you will be able to show the status of these two pins. So on the board that is typically around that people can buy, these two pins are connected onto an external two LEDs. In my case, this is a blue LED here and a red LED for charging. The actual mechanism on how this works is we have these two conditions where indicates that it's standby mode or charge mode. For standby mode, it simply means that whenever the charging current is less than 0.1 of the Imax, Imax being around 1 amp, when you connect this to like a 1.2 kilo ohm resistor or 1 kilo ohm resistor, that's going to be Imax, and 1/10 of that is going to be your standby threshold. Anything less than around 100 milliamps indicates standby condition. For charging, there are two conditions which have to be met. Either you have the Imax, charging current I in this lithium ion cell is greater than 0.1 Imax or greater than around 100 milliamps, or battery voltage is greater than 2.9 volts. Anything less than 2.9 volts, it's still going to be charging if this current is there, but it also will indicate that whether you're in trickle charge mode or whether you're in full charge current mode, in constant current operation. Okay, now that we have looked at the digital portion of this chip, it's time to consider the analog portion of it and how it starts up. So here's a scenario where I have turned off that current source IST, the startup current source, which is at the gate of the two upper current mirrors M1 and MC. So without that, I want to show you that this circuit will not work. So those who might be interested can follow along, or might skip to later portion of this video. But essentially, let's focus on that box with the purple box, and assume for a moment that we have a 3-volt battery or cell connected at the battery output of this TP4056. And let's also assume that initially during startup that this BAT mirror node, which is a negative input to the MA amplifier, is less than 3 volts, so that the MA output will basically drive to 5 volts, basically acting like a comparator. So the MR transistor will turn off, and we also assume that because of the fact that there's no current source to pull the V main CS node, the gate of these two large PMOS transistors on top are floating essentially. The only capacitance there, which is coupling to VDD. What will happen is that you have to look what happens to the gate voltage. So if you look at the amplifier VA on the right side, which is sensing the voltage at the current, the divider, the R1 R2 divider, then we have to see what the voltage, the positive voltage is going to be. So we know that if you look at the bottom two comparators, the 5-volt, the comparator that looks at the battery voltage, it's basically going to say output is going to be high because 3 volt is going to be greater than 2.9, and so its output is going to be 5, which is the node VBAT underscore greater than 2.9 volts, and that is going to drive the output of the NAND gate to 0. So the charge bar signal is going to be 0. I'm sorry, the input of that NMOS device is going to be 0, so it's going to turn off the charging, and so the MS comparator on the right side will be off. So the current mirror leg on the right side will be turned off completely. That means the current the resistor R1 R2 effectively will not see any current through them, and so the output, the VDIV voltage, which is the center tap of those two resistors, will actually float up to 3 volts or be driven up to 3 volts through the R1 resistor. That means that the output of VA is going to go up to 5 volts and essentially drive through the diode, is going to drive the Vmain CS node all the way to 5 volts. Even though it's going to have initially there will be a small voltage diode drop, but because there's no leakage path for Vmain CS, it will eventually reach 5 volts after some time, and it will basically turn off M1 and MC, and it will remain that way, nothing to pull it out of that condition. And what about the current source, the constant current amplifier? So since MR is off, the R program resistor will drag all those inputs of those comparators to ground, and if you notice that the CA amplifier positive input is actually looking at that R program resistor value, so that is going to go to 0, and depending on the selection of the battery voltage, that actually is, in this particular case, it's going to be 5 volts. So the input to the current CA amplifier negative input is going to be 1 volt instead of 0.1 volt. So essentially that is going to be driving a 0 at the output of the CA amplifier, and basically being reverse biased the diode, it will do nothing. So there's nothing here in this particular circuit that can turn this thing on. So that is case 1 where it's stuck off. Next, let's consider a slight variation of the case 1. So here I set bat mirror slightly higher than 3 volts. So if that is the case, then if it's greater than 3 volts, then the MA amplifier is going to basically servo towards 0 volts, because it's the positive input is less than the negative input, and so the MR transistor will initially turn on, which means that since there's a path to ground through our program, it will actually discharge that capacitor which is at the bat mirror node, and pull it down basically all the way to almost 0, and then essentially turning MA off again, and so its gate output voltage is going to go to 5 volts, and then MR is going to turn off, and we are back to case 1 where the whole thing is stuck at the off condition with the LED indicating standby. So this of course never happens in the real chip, because they do have a startup circuit, and we will talk about that a little bit later. But I think just I want to consider all the different cases that can occur in the startup scenario. Okay, so now let's look at situation where we have the battery voltage at 2.5 volts. So this is a different situation from before, where it was above 2.9 volts, where the charging condition was not asserted. Now this time it's going to be asserted because of the comparator, bottom comparator, which essentially output goes to 0, and so the NAND gate output goes to 5 volts. It turns on the right leg current leg, which makes the MS transistor on, and also charges the charge bar signal goes low, which enables LED to turn on. So right now we are in charge mode, but we don't know yet whether the upper part of the current source has turned on. So we have to look at that now. So since the right branch is on for the currents, the R1 and R2 have currents flowing through them, and the 2.5 volts at the battery will now appear as 0.73 volts at the positive input of VA amplifier. And since the negative input is 1.22, its amplifier's output will be driven to 0. for the CA amplifier, which is a current constant current amplifier, since we have the left leg turned off right now, we have the positive input of that amplifier at 0, and the negative input is going to be at 1 volt. Or is it actually 0.1 volt? I'm sorry. So that's a error on this thing, because the battery voltage is 2.5 volts. It's going to be in the trickle charge mode. So this is going to be 0.1. In any case, doesn't matter. The output of the CA amplifier is going to be 0 volts. So we have to look at what V main CS is doing. So normally for a PMOS current mirror, it's usually decoupled to the supply, and assuming that there's no charge on the capacitor that is shown between those two nodes, when the supply rises, it's going to drag V main CS along with it, since there's no way to charge that capacitor. So it's going to maintain the same potential difference, which is 0 volts, and so it will come up with VDD, which means that for most cases it's really going to be turned off. M1 and MC have no way to really have a large potential difference to turn it on in the negative sense, the negative potential, which can allow the gate to have a lower voltage than VDD. So since we also have the 0 volts coming through the diodes, and those diodes are heavily reverse biased, it's unlikely that they can actually pull that V main CS node lower. So essentially it's going to remain stuck unless somehow there's a very lucky situation where V main CS actually is at a lower voltage, and then it starts up those two current sources and pushes current through that to the BAT MIR node, and then once that happens, it can actually turn on the MA amplifier, and there'll be a leg paths to all the way to our program resistor. So the left leg could potentially turn on if this lucky situation arises. So that's why I'm kind of saying that case 3 is are you feeling lucky today, because it's really not, you cannot depend on this for the chip to wake up. And so that's why we come to the case 4, which I'm not going to show you here, but that is when you turn on when you put that current source IST, which is shown there, which is crossed out in this particular schematic. If that is there, it can actually pull V main CS towards a lower voltage, essentially turning on those two PMOS current mirrors on the top, essentially turning on the left leg first. Once that happens, the MA amplifier will equalize those voltages, and then everything turns on, and I think the chip will then at that point start to work properly. So that's really what I wanted to say, this long-winded discussion about the startup thing. So now that the chip has started up, let's see what happens after that. So initially, let's say the battery voltage is 2.5 volts. The iStart current source has started up the loop, and everything is working. So initially what happens is that since the initial battery voltage is 2.5, it's going to be in the trickle charge mode because of the comparator shown below. It's going to essentially set the bottommost comparator actually, because the battery voltage will force it to in the low charge mode, which is a 0.1 volt reference, which goes into the CA amplifier. And as the current starts to charge up the battery, it will eventually reach 2.9 volts, at which point the VBAT will then switch over to the 1 volt reference for the CA amplifier, and the R program resistor will continue to increase the current all the way up to 1 amp, but 100 milliamps be flowing, 1 milliamp be flowing in that leg, which is 1,000th of the output current. And eventually as this battery voltage builds up all the way to like 3.9 or around that value, the output impedance of the current source, MC current source, or the internal resistance of the battery will start limiting the current that can actually get into the battery. So that already trying to approach the constant voltage mode, and that will finally occur when the R1, R2 VDIV voltage reaches from 0.73, it ends up at 1.22 volts, at which point the VA amplifier will start to control the loop. So that will then regulate the V main CS voltage to maintain 4.2 volts at the battery, but continue to charge the battery until the current starts to drop further, and it will eventually, the current will drop below 0.1 of the Imax current, which is 100 milliamps at the output, which will then terminate the charging, because the second comparator from the bottom will then indicate that the current has dropped below that value, and it will switch into standby mode. So on the left side you can see I have indicated in the beginning we have the red circle around the bottom LED, which is in the charging mode, will go into the standby mode on the top LED, and the black indicates that the LED is off. So I think this pretty much covers the functional aspects of this TP4056 chip. There's one more thing I will want to show you, and that I'll go back to the board to describe that feature. So the feature that is to me doesn't seem to be described, or not sure how it works, is the automatic recharge feature. That basically means that when this cell voltage drops to below 4.1 volts, it actually this loop has to work again, and that can be demoed in various ways, and I'll show that. So that particular feature, I don't see that being implemented here, at least in this way this is shown. If somebody has a better idea, do comment on that. So one thing I forgot to mention, we do have also a shutdown mechanism. The shutdown mechanism works as follows. So if you disconnect this R program resistor, then all you're left is with a capacitive kind of network here. There's no active pull down. So this leaker, or this shutdown current, actually is a small current, again few microamps. It would charge up this capacitor, and this voltage would continue to rise as it charges up. Once it reaches a value over 1.22 volts, this signal, this comparator will essentially will assert. In this particular case, this being higher, it will go high, and I think that should be shut down, not shut down bar. And then essentially the chip will go to a power down state where the total current consumed from the supply is around 50 microamps or so. And then in order to bring it back into working operation, you've got to connect this resistor back again. So I think if you're using the discrete chip in a system, you can do that, but if you're using one of those boards that come along, then this is a very tiny one resistor which is hard to remove or to program. So I think this is best not used in typical applications. It's possible to actually simulate this circuit using discretized versions of these various blocks, and you have to come up with some values which make sense for these resistors, so you get the right voltages in this ladder, and also for here. That's fairly simple, assuming typical chip type impedances. You can put in these kind of values, they probably will be fine. You can also replace these amplifiers with ideal op amps, or with voltage limited or slew limited type amplifiers. For the diodes, you need some kind of a model to run it. I just use some discrete diodes. So basically this circuit will not mimic an IC type operation, but it will mimic the overall functionality if you simulate it, and that's what I will try to show in a little bit later. So here's a very simple setup of this TP4056 board. I have the one with the under voltage protection, and I have disabled that feature by shorting out the battery minus and out minus pins, so there's no sensing of the current or voltage for that particular chip to do anything, those two chips on the right side of the board. So only thing that is active is the 4056. And then I've used these wires to connect it to a capacitor, which is around a bunch of capacitors to approximate a lithium ion battery cell. So this is about 20 millifarad, which is pretty large. And here's electronic load. Right now the battery is this capacitor is charged up somewhat, and it's actually slowly discharging through its own leakage resistance. And so either this leakage here or its own internal leakage resistance. So it was initially charged to 4.2. It's down to about 4 volts after about 5 minutes or so. So I'm going to observe the output voltage of the 4056 on the scope. Right now it's reading around 4 volts right at the top. There are two cursors. One is for the high 4.2 level, and one slightly below that is the automatic recharge level, which is around 4.1 odd volts, I think. Right now there's nothing connected here. The USB will plug in, and then this will basically recharge it all the way. Then we'll see what we can do is to basically discharge this cap and then see how the startup looks. Look at the initial trickle charging, and then the constant current high charge, and then the voltage mode, and then discharge, and so on. Okay, I'm about to plug this in, and you'll see the voltage jump up to the maximum value, and it'll stay there. Right now the load is off, so nothing's going on. It's fully charged. The standby mode, as I indicated, once it reaches 4.2 volts, it will not. It will basically go into standby mode. No more charging is occurring. So this is around 4.19 thereabouts. So now if I do a constant voltage mode, I can show you what happens at different voltages as this capacitor is set at that voltage. This board will essentially do what it's supposed to do at those different levels. So let me set it into voltage mode, constant voltage, and now let's set the voltage to something like 2.8 volts, where it's supposed to be in trickle charge mode. Okay, let it be at 2.775, that's fine. So now once I turn it on, you can see it discharged, and then it basically came up, and it's now at 2.7 volt, and it's charging at well, actually it's charging at the full current rate, which is interesting. So the reference may be off a little bit. This should be around 1/10 of this. So let me go down to a slightly lower voltage. Alright, so now you can see at 2.64 volts or so, it's now maintaining that 2.64, of course, this voltage source, and then you can see the charging current is now dropped to 95 milliamps, which is what it should be doing. And now I can fully discharge it by, let's say, if I short this thing out. So it's shorted out, and now it will quickly come back up and fully charge up to the 4.2 volts and maintain that. There's no load at this point. Alright, so we can now work in the constant resistance mode here and see what happens. Okay, so now we are in the constant resistance mode. There's 5 kilo ohms of resistance. Turn it on. So now you should see some dithering going on. I don't know why it took so long to enter that mode. Anyways, now you can see that sawtooth waveform where it's going up to 4.2, and then it's discharging down to that 4.1 volts. So that is going on continuously, and this chip is now also, you can see the lights blinking, the recharge light, the charge light comes on very briefly, as it's a very small energy in this particular cap, so it quickly charges up to 4.2, and then it decays back because of the load discharging it. So that seems to be working. So if I can actually speed up, show a little bit more of that waveform. can see that clearly here as it's sweeping through that up and down. We can also increase the rate by decreasing the resistance. I set it at 500 ohms. Again, you can see that it's much more rapidly discharging now, and essentially it's the same behavior. So but this automatic recharge feature, really I couldn't explain it on the circuit schematic, so something I don't know, it's probably not described. So what I thought I would do here is to show a little bit detail on the discharge mechanism. As you can see here, this is 100 millivolts per division, so I offsetted the scope quite a bit to get this kind of amplitude on this discharge and charge mechanism. You can see that at the beginning, when the charge comes on, it immediately jumps to some value, and then it then goes into this slower charging mode right at the edge here. And that is because it's not able to provide the full amount of current, and then this jump is due to the internal resistance of the cell. We can calculate that based on this jump value and the current that is going into the charging battery. And then the discharge is really determined by the resistance over here. That's right now 200 or 300 ohms, much slower. So one interesting thing is really you can determine your internal cell resistance by looking at this initial jump. The smaller that is, the lower the resistance. In this particular example, I would say, given that this is 100 millivolts per division, this appears to be around half of that, or maybe 3/4 of that, maybe 60 to 70 millivolts, or that would mean about 70 odd milliohms of resistance in this particular capacitor. Okay, so this finally brings us to the conclusion of this video. I think it took way too longer than I expected, and I probably spent way too much time digging into the depths of this chip. Not sure if it was worth it, but to me it was just educational. I didn't, of course, fully understand one of the aspects of this chip. I did simulate it, and I was going to show the simulations, but probably I'll do it for some time later if people are interested. Do let me know, and I can create another video talking about the simulation aspects of it. But I think it was pretty useful for me anyway, to figure out how this thing worked, and I got to test some of it as well. So thank you again. See you next time. Bye.